Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about RNN or recurrent neural networks, which are very important part of neural networks and deep learning if you want to work with sequential data or time series, like stock market prediction, speech recognition, and so on. Okay, so let's start from vanilla neural networks. So in vanilla neural networks, we have the architecture is something like this. So we have some inputs in here, and we get one output. So we call this one-to-one neural network. Okay, so this is a one-to-one task. We have one input and one output. When we have recurrent neural networks, or that they are for processing the sequences, we could imagine different tasks. For example, we could have one-to-many. Let's say you have an image, and from the image you want to do image captioning, which is in fact having a sentence about that image. So if you consider a network that gives you some words about image, so you have different words to make the sentence about that image. So it is a one-to-many task. For many-to-one, you may have some different frames from a video, and you want to let's say you want to recognize the activity in that video, or activity recognition. So it could be many-to-one. Okay, or also you could have as another example, you could have some different words and pass to the networks to get the context, or some kind of classification on those words. And you could have many-to-many task, which is in fact, for example, let's say you want to have a translator. For example, in Google Translate, you could put some sentence, and then as the output you will get some other sentence in a different language. So in this case you have a many-to-many task. So and they could be in two forms. In one task, in the first example, as you could see, first we will get all of the inputs, and then start to create the outputs. For example, when you entered the input sentence, the network, after entering that sentence, could start to produce the output. So it is the structure like this. Or you could have a many-to-many. So let's say you want to classify a video based on each frame. So in each frame we want to have a prediction for the output. So it is a many-to-many task with this kind of architecture, because we have, for each frame we should have one output. This is an example of in fact the need for RNN or recurrent neural networks. So let's say we have, so this is a description about a sport, which could be football or basketball, and we want to know which one of them has this description. Okay, so this is an example of the case that we could use RNNs to solve this problem. Another word for text analysis. Or let's say you have the stocks as the input of your network, and you want to know whether to invest on something or not, or to invest in some specific company. Okay, so the input could be the vector and the output could be scalar or vector based on whether we should invest or not, or invest in what company. And also, as I mentioned, in speech recognition, we could use RNNs to do speech recognition and convert the speech to text. Also, sometimes it is interesting to look at non-sequential data as sequential data. For example, let's say you want to generate this image, or let's say you want to predict the number. So in this case, one way is to just look at small patches one by one, and then somehow do many-to-one task to know and find out the context of this image. Okay, now in order to represent the things simpler, we represent the neural networks with these blocks, as you could see. So we represent the set of neurons with a block that it is more compact and easy way to represent them. Okay, so for the stock predictor, one thing that we could do without RNN is time delay neural network. In time delay neural network, we just consider few days. So in this case, we just consider 3 days or 4 days to make the prediction for the last day. Okay, so the input of the network is the first day, the next day of that, and so on, and then predict the price of the stock based on those inputs. Okay, and as you could see, when we want to predict for this time step, we again consider the last 4 input and then make the output as a prediction. So this is the time delay neural network, and so on. So as you could see, we just consider the last 4 inputs to make the prediction for our current time step. So in general, we call these models finite response models. In other words, we make the prediction based on the input of the current input and some n last inputs. So in other words, for example, in this example, n is 4. So we make the prediction of t based on the input of t, the input of t minus 1, the input of t minus 2, and the input of t minus 3. Okay, so this is this means that we just consider the last 4 output for the current prediction. Okay, now let's say we want to consider more time steps. Okay, so when you have stock market, you have lots of different steps. So let's say you want to make your history larger, or you want to decide or predict the current prediction based on more values from the past and consider more history. In that case, you should have more complex network, because in that case your network should be able to handle these 7 different outputs. Okay, in previous case we consider 4, now we consider 7. So it is actually make the network more complex, and so it is kind of hard for this kind of networks to consider long-term dependencies, because it makes the neural network more complex, and we need more CPU and memory to do the computations. In fact, what we want is kind of infinite memory. In that case, we want to consider all of the past to make the current prediction. So when we are in this step and we want to make a prediction, and this is the past, we want the network to consider all of the past to make the prediction for this time step. Okay, in that case we have infinite response systems. Okay, so as you could see, we consider all of the time steps through infinity, so we consider all of the last time steps. Okay, so one possible way to do that is to use NARCs systems. So in this case, as you can see, so these are inputs and this is the output from the previous step. So we pass this and the input of the network to a network, and then create an output or make the prediction, and again pass that to the next network with the input, and so on. So this is one way to do the recursion from the output. Okay, and in fact an input from the time step 1 could affect on all of the other time steps. Okay, so this is kind of infinite memory, because this could affect on all of other steps, which we are more interested in. Okay, and for the architecture of that, actually we have different kind of architectures. So in this case, as you could see, we could pass this output to different other layers. Okay, in other words, the output y at time t is computed from the past k outputs. Okay, so when we want to make the prediction in here, we pass these and consider these outputs to make the prediction for this output. And the same thing could happen for x. So this is a more generic form of NARCs network and more complicated thing. An alternate model for infinite response model is the state space model. So in state space model, we actually create an state for the model. So we have H, which is in fact shows hidden. So we have some hidden states, and the hidden states times the T is defined based on the input, based on the current input, and the current hidden state, or we could say that the initial hidden state or previous hidden state. So we update the hidden state based on a past history of that hidden state and the new input, and then make the output or make the prediction based on a function of the hidden state. Okay, so in that case we call these models, if they are neural network, we call this recurrent neural networks or RNNs. So in these networks, the states summarizes information about the entire past, because when you have something like this, the first input could affect the hidden state, and the next hidden state could affect the next hidden state, and so on. So in this case, the first input could affect all of the next hidden states. So in this case, we have something like this. We have, let's say we start by an initial hidden state. So we have an hidden state, initial hidden state, and an input, and then make the prediction. And again, now we could see that we have a new hidden state, and based on this new hidden state and the input, we make the prediction, and so on. So in this case, this input could somehow affect this prediction, because this input could affect this hidden state, this one could affect this hidden state, and so on to here, and this hidden state affect and produce the output. So in this way we are making some kind of memory. So actually we could show that with this kind of architecture. So we have input and we have an RNN, which this arrow shows the hidden state in interaction of the RNN with itself, and this is the output. So the hidden state, the new hidden state, is a function. Is a function. So probably nonlinear function of the old state and the new input vector. And you should note that after in each time step we apply the same function to get the hidden state. So for example, in here, when we want to get h2 by applying a function f on h1 and x2, this function is the same function as in here, so we apply the same function to create the hidden state in here. Okay, so we don't change the function through time. So in vanilla recurrent neural network or in vanilla RNN, the hidden state is the tangent hyperbolic. So this is the nonlinear function, which is a function of its weights. So we have some weights for previous hidden state and some weights for the new input. And when we apply this nonlinearity, we could get the hidden state. And the output of the network is determined by some weights times the current hidden state. Okay, so this is a really simple thing, but a really important thing in RNN. So actually this is a single hidden layer RNN. So we now know about this and how this works. But we have also multiple recurrent layer RNN. In this case, we have two different hidden states. So when we have a hidden state in here, this hidden state could also create and affect another hidden state, and then another hidden state could create the output. Okay, so in this case we have a two hidden state at each time steps. Okay, so these are different time steps. Also, we could create more complex architectures. So we could create the next hidden state with both the hidden state, the first hidden state, and the input of the current time step, and so on. And also we could have different, more complex architectures, but actually the simpler one, or in fact the simplest structure, is the most popular one, and it is in fact used in RNN. So in this case, if we have two hidden state like this, so we could write the hidden state, the first hidden state, as the nonlinear function over the input. So this is a function of input and the previous hidden state of itself, and for determining the hidden state of the next hidden state, it is determined with the input of this, which is the previous current hidden state of previous cell, which is this term. And as you could see, this is 1, but this is the input to this hidden state, and we have a term for previous hidden state of itself, and also a bias. So we have the same bias. We have another bias in here, and also the output will be determined based on just this hidden state. Okay, so we have this hidden state and a bias. Okay, so now let's see the computational graph of RNN. So in fact, we have, if this is a more, I think more simpler representation of RNN. So we have hidden state, the initial hidden state, and we have the first input. Then we apply some nonlinear function to get the next hidden state, and again for the new input we apply for the new input and new hidden state we apply the nonlinear function to get another hidden state, and so on. And as I mentioned, we use the same weights for all of them. So we use the same function of W, which implies that in fact we use the same weights for all of the time steps. And so this is in many to one task. So we want to have an output in the T in the T step. So we just have an output in here. But in many to many, we have output in the first time step, in the second time step, and so on. So if this is the output, we have a loss for the first output. If we want to train the model, we have some loss for the first time step and so on. For the second time step, we have some kind of loss based on difference between the ground truth in the second step and now for the output of our model. And to calculate the total loss of the model, we could sum over and add all of these losses together to get the total loss of the model. And for one to many, we could have something like this. So we have just an input in the first time step. Then we have just hidden states that determine the output. Okay, so this is one to many. For sequence to sequence or many to many, we could have we could consider that as many to one and one to many. So in this case, we could have a many to one, which is in fact encoding the input sequence in a single vector or in single state. So we just pass the inputs through an RNN to just encode all of them into the hidden state. After that, we want to create the outputs from the single hidden state. So it is a one to many RNN or one to many task. So this is some kind of encoder because it encodes the inputs into one single vector, and this is kind of decoder network, which is decode this single vector or encoded vector to different words probably. Okay, so let's see a language model example. So in language model, we want to, in fact, compute the probability of some different words. Okay, so we could sometimes model it. In fact, we could model that with based on conditional distributions. So for example, we want to know the probability of the first word, the second word in a sentence. We could use, we have seen these rules in the probability part of our course, so we could decompose this into these terms. Okay, and this is actually used for machine translation, spelling correction, and so on. So for example, we could say that the probability of the dog is big is more than big is dog, because it does not make sense. So the probability of this is less than the probability of a correct sentence. And also for the word choice, for example, we could say that the probability of it was late afternoon is greater than the probability of the sentence it was today, because it doesn't make sense so much. So when we train the language model, means that we want to obtain these probabilities. We could have some kind of recommender system for you for machine translation, or recommend to you some using different words in your sentence to make your sentence more sensible and so on. Okay, so we want to have a model that we give that model a character, and we want the model to predict some other characters for us. Okay, or at higher levels we could do the same with words if we encode the words properly. So in that case, after observing W1 to WK, which could be characters or words, it predicts the next word based on these words. Okay, so we could see that as so we have some inputs as vectors. Let's say these are input vectors. These are the sequence x1, which is the input at the time step 1, and so on. And the hidden state, we know that now how to calculate the hidden state, and the output is getting the softmax over the weights times hidden state, and we could say that it is some kind of approximation to estimate the probability of what we are looking for. Okay, so to train the model, we actually, or for the loss of the model, we use the cross entropy loss for each time step. So for a specific time step, we use a cross entropy loss, which is we use in also different classification tasks, if you remember. And so the cost function over the entire sequence, or in different time steps, first and to t, will be the average. We just get the average over all of these loss in different time steps. Okay, so let's see an example at character level language modeling. So let's say the input layer, or the inputs, are H, E, L, L. Okay, and so the sequence is hello. So we code the HEL as you could see in here, it is a one-hot encoding, and also O as 0001. Okay, now let's see how could we apply RNN on this. So we have H, and we have the hidden state in here. As you could see, based on the initial hidden state, we could apply these with some, let's say with some for now you could consider that we know what the optimal weights are. So with some weights we just calculate this, and so now we have these. Okay, and so on. So after that, we could create the output based on by applying the matrix of the weights of for getting the output, okay, or WHY. So in this case, for example, you could see the output, and the second, for example, in the first step, when we pass H to the network, it predicts E for us, because we trained the model on hello, or on a sequence. So now the language model is trained. So now the output shows us the next character will be probably E, or the language model predicts for us that the, after H, we probably have E as the next character, because the model just learned on hello, so it just saw E after H, so it tells us the most probable thing after H is E. And if we get the E to the network and we have the hidden state, it tells us it is L. The next probably the next output will be L, and so on. Okay, so for the last input, if we give the model L, it tells us it is O. Okay, so it is some kind of character level language model, but in fact, in the reality, to get the output or to generate a word, if you have H in here, then you get E from model, then you could pass the output of the model to as the input of the model in the next step. Okay, and that is so cool to get L and so on. Okay, so this is probably the thing, but in more complex thing, you could think of Google when you want to search something in Google. So for example, you just put let's say D in the search bar, then Google runs this network and create D, and pass D to their big network, because Google used lots of different networks and probably maybe different algorithms, but now we could have some kind of toy example and the basic things that to understand it better. So it passed D to the network and get the output, and pass the output as the next input of the network, and so on. And maybe it gives us this recommendation, DSN, as Data Science Nigeria, or something like that, okay, based on what is the most probable thing for you, because based on your search history and so on. So it could be much more complicated, but now you have a grasp of basic concept. And there are some interesting things in deep learning for language modeling. For example, there are some networks that trained with Shakespeare, and this is the output of networks through different epochs. So by training the Shakespeare at first epochs, the output of network is not really good and doesn't make sense, but when we train the model more, we could see that now the model creates fun and some sensible sentences, which is really interesting. Also, there are some other fun things that train the network on some LaTeX sources and to generate some papers. Okay, so these are the papers created by and generated by just an RNN. Okay, and also to generate codes, there are some models that trained on them. To visualize the cells and to visualize how the cells work, also there are some researchers, for example, in code detection. These are the cells activities. So for example, for code detection, we could see that when we have the code, the RNN is very active in these regions, okay, because it is a code detection task. Or if we have line length tracking cell, the end of the lines are so important, so the activity of cell is so high in the end of the lines, and so on. So we have different examples from this. Another example of RNN which is useful is image captioning. So now we know what is image captioning. In this case, we have an image and we want to generate a sentence for that image. Okay, so in this case we could have a neural network, so we could pass the image to that neural network to get the feature vector, and we could pass the feature vector to RNN as the first hidden state, and so on, and we could get the first output. And as you could see now, it is so simple to just get some sample from the output, because the output of this is some probabilities over different words probably. So we sample from those outputs, and then again by the next hidden state we create another output and sample from those, and so on. Also, you could have the end token as the finish. So let's say we have in your words, you could have hat and other things, and for the end of your sentence, or to know when you have end, you could have and or some certain character to know where you should terminate, or where the neural network should terminate its sentence. And also, so this is about image captioning, which you want to get some different aspects of an image, and also you could get some sentence about an image with neural network with RNN. And also there are some failures in these cases. As you could see, they are some kind of funny. To train this neural network or RNN, now we want to talk about the training of that RNN. In forward pass, we know how to compute the output of the network, but for the backpropagation, we could have a backpropagation through time. So we just add all of the losses in different time steps to get the total loss. Okay, but the total backpropagation through time is really computationally expensive if the number of time steps are a lot. So in this case, we could use truncated backpropagation, which, for example, you could consider just, let's say, 7 steps, 4 steps, or whatever, to just consider the loss in those time steps and train the network on those steps. Okay, so this is the first part about the RNN. We have another part which we talk more about RNNs and LSTMs and GRUs units, to learn more about them and about their capabilities and incapabilities. So I hope that you enjoy from this session, and we will see also an example of RNNs in Keras. So don't worry about it. See you in the next session. Bye.